let's get started here. Overall, you know, these weren't easy. I mean, we're throwing out some stuff here that we want to be able to do that you're going to see again. But the reason I've picked out these things is they are challenging. I mean, and then the story problems like Appendix G. You know, I often thought, I mean, when I look back at my high school, and I took calculus in high school as well, and I thought Algebra 2 was one of the harder classes, to be honest with you. What I thought was hard about it were the story problems. I mean, that's what these kind of are. And it was because they're hard, getting them set up. And that was the whole purpose of Appendix G. Is I've said this already this year, is that there are going to be times, many times possibly, where the calculus is not what's tripping you up. It's the trig or it's the algebra that's the problem. Because if we can't get through those things, we can't get to the calculus part of the problem, right? So if we can't set up a formula for the profit when we're selling mugs, then we cannot find the maximum profit, which is what that problem would be about in calculus. If we can't set up the time equation that it takes the snowmobiler to get to the gas station, then we can't figure out what route he should take to minimize the time to get to there, which is where the calculus comes in, right? So we want to be able to do that. So that's one of the things, and probably one of the more challenging quizzes we take all year are the ones that involve those kinds of problems, setting them up, because they just can be challenging to set up. So don't determine your fitness for calculus based on how hard or easy. I joked with Casey about how this was the easiest homework assignment we'll have all year. That's not true, but you know, so don't. And even the first quiz we take, I often tell people after the first quiz, it's not indicative of how you're going to do if you do poorly on the first quiz. Actually, the first quiz is not going to have any calculus in it. It's going to be, you know, the things we want to be able to do with functions and so forth, and remember and be able to do with functions. And I talk about remember like from an old course, previous course. Well, we're looking at it in different ways possibly too, how we want to be able to work with them this year. So people have done well even after maybe not doing well in the first quiz. I mean, and I've also had people do really well in the first quiz who then get cocky and think that they've got it made in the shade, and then they, you know, don't do well later either. So it works both ways. So the main thing is the effort and how willing you want to be to work on this. And sometimes with seniors it's interesting. I mean, because, you know, you're getting to that point in your high school, career where you're starting to think ahead. I mean, in Bearcat time, you're talking about college applications, right? And we're going to be getting, you know, after before Christmas, and then after Christmas you're applying, you have deadlines. I mean, so you really start thinking ahead of the next phase, if you will. And so the time and effort you want to put into your high school stuff starts to maybe dwindle right at the same time you're maybe facing some of the hardest classes you've had in high school, like AP Calculus or AP English, you know. So it really comes about an attitude and a mindset of how hard you want to work. And I'm sure you know, I'm preaching to the choir a little bit because you're here, right? I'm sure you know some classmates who probably should be in here, but are not, because they're going to kind of skate through their senior year, right? So probably not the best decision, and probably may come back to haunt them, you know, in college as well. But that's beside the point. All right, so let's go through. I've picked out a few here that I kind of want to hit that I think would probably answer most of the questions that you may have on here. If I don't, maybe see me individually, and don't be afraid to raise your hand here and ask me something that is getting by you as I talk about this. But so I've tried to pick out a few here. So on 28, so one of the things I really want you to be able to do on our next quiz, which is Tuesday, by the way, next Tuesday, okay? Our next quiz, there's not some great big field trip or anything where everybody's going to be gone on Tuesday, is there?
I wish there was.
Okay. Well, because then we'd have the quiz on Monday, so that wouldn't be good. So you might not want to do that. Okay. So we jam everything in and get it done by Monday. All right. Well, one of the things I want you to be able to do is read function notation. Everything we do in calculus is about functions, okay? Or almost everything we do deals with functions. So this function notation is critically important. So understand that this is really an ordered pair. In calculus, we will rarely write an ordered pair like this, right? To us, that's an interval. The interval from -1 to 5, right? Our interval notation. Now, you'd be able to tell the difference in context of the problem, but we will not write an ordered pair this way. We'll write it this way. That is an ordered pair. This is saying you put an x in, or you put a -1 in for x, and you get out a 5 for the output. Now, I won't use x and y that often. Sometimes I will, but I'll use input and output, right? Those are kind of the similar things, but it doesn't always have to be x and y, right? So this is our input of -1, and we get an output of 5. So that means I take my equation, put the output equal to 5, and I put a -1 in there, and I get this. Now, what I wanted to say about this, you were supposed to solve for a. So just divide this, and those of you that weren't here, and if you didn't get a chance to watch the video, I said these should really all be no calculator kinds of things. I don't want you to type in e to the 0.2 in your calculator, right? I mean, I understand that we could do this on our calculator, and that part's easy. And I wrote that wrong. So what I'm going to do there is divide by, divide by e to the -0.2. I'm just going to divide this over. And to be honest, you could probably leave that there. If that's all we wanted was a, and that was on the quiz, that'd be fine. You could just leave it just like that. Okay? Now, a negative power, what's that mean? It flips up, right? I mean, so this would really be 5e to the 0.2. Now, why is that important? Well, there's going to come a time where we want to do some calculus to something, and the calculus will be easier to do if our expression is written in its most simplest form, or at least written in a certain way. So we want to be able to rearrange expressions using algebra rules so that it'll make our calculus work easier, okay? And again, I'm talking about in a no calculator kind of situation, so just leave it just like that, okay? All right, jumping around here a little bit. So I picked out 52 as well. I helped a few people with this one, but you were supposed to use some log properties here. So you were given this, and you were supposed to do this. Now, what I would do is I would set this equal to x, like so, and then I would write this as an exponential. 2 to the x equals a. Okay? And over here, I know this is 4 to the 2.1 equals a also, right? So both of those equal a. Well, that means 2 to the x would have to equal 4 to the 2.1. Now, keep in mind, some of you might be sitting there saying, well, man, I thought of that an easier way or a different way, and I got the same answer. That's very possible, and that's good. If you did, it means you have a good understanding of what you can do with logs, and it probably was just fine, okay? So it wouldn't have to necessarily be done this way, but I'm kind of doing it maybe the way that accentuates the rules that we have and a way you could follow without having to know a whole bunch of stuff. You've got to be able to convert this into exponential form. And then how can I equate these two? What do I do with that 4? Yeah, let's make it 2 to the second power. Does that make sense? Because what I'm trying to do is get like bases so I can compare. Now, what's the rule when you have a power on a power? You multiply. Now, notice then the numbers are easy. So in a no calculator situation, you'd be expected to do this. So what we get is 2 to the x, and this is 2 times 2.1, which would be 4.2. So x is clearly 4.2 in this case, right? And x, of course, was this, right? The thing we were looking for. Okay? So just being able to convert exponentials and be able to rearrange bases and stuff like that is just something that's kind of a good thing to be able to do. All right? If you never quite get the hang of that, doesn't mean you can't do calculus. Okay? I mean, it'd be nice if you could. It'll make life a little easier in some cases, but it's not the end of the world. Okay? I picked out 45. Oh, and you know what? I wanted to do another one here. There's one there, and this was an odd one also. It said log 4 of 16a. This was an odd one. Well, one of the rules of logs is what can you do when you have a multiplication here? No?
You can add.
It's add, yeah. So we can write it out as an add. And so what that would end up being is that. And then this, of course, was 2.1. And what is this? 2, right? Because remember a log, it's 4 raised to the what makes 16. 4 raised to the 2 would make 16. So 2 plus 2.1 is 4.1, right? So there's just a variety. We only did the evens, but there's some other ones on the odds. It wouldn't be bad to look at just to make sure you could do it. But anyway, I had that. And so here was another even I had. And they had this. And what would you do with this? Anybody have a thought? Something come to mind right away? Kind of springing it on you, but...
just cancel out the natural log.
Sort of. There's one thing you have to do. What would you say your final answer would be? You're close.
X equals 1/2.
Well, we're not finding what x equals. We're finding what this thing is equivalent to. The answer is x squared. Bring the 2. Remember that rule where you can bring the power down? Because that 2's there, we can't do... Now, one thing we talked about yesterday is e and natural log are inverses of one another, so they kind of cancel each other out, if you will. Now, there are some domain issues when we cancel things out. We got to be a little careful. We'll get into that later in the year. But this 2 can get put right up into there, which would be e to the ln of x squared. And now we can say, oh, and the e and the ln kind of undo each other or cancel each other out. So that just becomes x squared. Now another way I could have done it is this. I could have said, well, let's just set that equal to y, right? I don't want to use x because it's already in there. So let's set it equal to y. And now let's change that into a log, okay? It's an exponential. Let's change it to a log. So that'd be log base e, right? This is the base of y is equal to 2 ln x. But what's log base e? ln. So this is ln y equals 2 ln x. Okay, so they're not quite equal. That 2's a bother. What do I got to do with it? Move it into there. So no matter how you do this problem, you've got to understand you can move that 2 into there. So now you got ln y. Oh, okay, so y is equal to x squared. Okay, so this thing was y, so the answer is x squared. So we could have went about it that way too. All right? All right, 58. So now we get into these ones where we have to do some solving, because we're going to get into some problems where we deal with exponentials. One of the things we'll study is something called differential equations. Differential equations. And differential equations in college, if you're going to go into engineering or something, after you get out with the calculus sequence, the next class you take typically is differential equations, which is kind of like solving quadratic equations, right? There's going to be some rules if you have something, a differential equation. Now, a differential equation is an equation that has a derivative in it. Remember we said derivatives is something we're going to study. So you have these equations. One of the most famous and common differential equations that exist is an exponential type equation, like exponential growth and decay. So we're going to get into some of those, and we're going to have to solve these exponential growth problems. So we'll be doing some of this kind of work. So what they're saying is the output is equal to 80. They don't give us an input for x. They just say the output is 80. They want us to find x, right? So we set 80 equal to 20e to the 0.1x. Now, we're not using our calculator. If we were allowed to use our calculators here, then what I told you yesterday, and I don't know if this was in the video, probably wasn't, but if we were going to use our calculators, we would just go in and hit solve, and tell it to do it, right? So this is if we were in a no calculator situation. So we first have to do what? We have to divide by 20. See, so we would just go into here, and we would just go, if this was a calculator problem, we would just say menu, algebra, solve, and we would type that equation in and let it solve. Okay, so we're working in this in a no calculator. So we divide by 20, we get 4 equals e to the 0.1x. Now those of you that like doing log, just converting it to log form right now would be just fine. Some of you would be able to look at that and just say, oh, 0.1x is going to be ln 4, right? If you're good with that, that is true. I'm going to do it as if I take the ln of both sides. It's just a little more, it's something that's just probably easier to remember and not have to worry about correctly doing it. Just do the log of both sides. But watch what happens here. What can we do in this side? Bring the exponent down front. We get 0.1x times ln e. What's ln e? I think I said this in the other class. ln e is, you said cancel, but what's ln e? 1. And what's ln1? No? Nice try. 0. Those are two log values you should just know. You just need to really know those. Now, why is it? Remember, the base here is e on natural log. E to the 1 makes e, and e to the 0 makes 1, right? And so that is true all the time. Now, it's actually true on any log. If I do log 2 base 2, that's 1, right? Log 3 base 3 is 1. Log 4 base 4 is 1, right? And any log of 1 is 0. 3 to the 0 makes 1. 4 to the 0 makes 1. 5 to the 0 makes 1. So log of e is 1. Log of 1 is 0. Those are ones we just want to always have in our pocket that we just know. So ln e is 1, so it's basically gone. And so we end up, at this point anyway. Right? By doing that, we end up at the same point. Now divide by 0.1, which is the same as what? Multiplying by 10. So you'd have that. But I'd even accept if you had ln4 over 0.1. I would accept that. I probably shouldn't, but I would accept it. Some college professor would think I'm crazy for letting you get away with that. But okay, ln4 divided by 0.1 would be okay. But it's really 10 ln4. Now, if you type that into your calculator, you guys probably already know because I showed the other day, but if somebody's got their calculator real handy, type 10 ln4 and hit equals. Type 10 ln4 and hit equals. Now remember, it's going to try to give you an exact answer, so it's not going to give you a decimal, right? So it should just spit out 10 ln4, right? But it doesn't. What's it say? It says 20 ln2. Why? Because 4 is 2 squared. 4 is 2 squared, and then it's pulling that 2 down in front times a 10 and making 20 ln2. So that's what drives you nuts on the AP test in the multiple choice section. You'll have this problem where you have to solve, you'll go through all this work and you'll get 10 ln4 and then you'll look at the choices and it's not one of the choices. 10 ln4 is not one of the choices, but 20 ln2 is. So you'll have to know that log property to be able to answer the question. So you got all this so the AP test is really good, I mean if you consider that good, it is really good at testing multiple things within one question. Okay, they'll throw things like that in there to test you on that. All right, so move on to 62 here. And I apologize for those if you think this was all really easy, but I got a sense maybe this would be time well spent. So here you've got an equation and they give you 1 point on there because there's an unknown. There's this k that we don't know. So for us to find that unknown in that equation, we need a value to work with. That's called, in our problem, like an initial value or something like that we'll talk about. So we know 1 point, we can find out what k is. So we do it. So we plug a 1 in for x, which I did there, and put a 10 out here for the y, or the output. Okay, so we have to divide by 20, which is 1/2, okay, equals e to the k. And again, some of you will just look at that and just know, well, that's ln 1/2 equals k, right? You can just, from here, you can just, from here you can just go right to there. If you convert that exponential into a log, right, you can just do that. Or I showed doing the ln of both sides, right? And here you bring the k down in front, you get k times ln e. And again, we said we know ln e is 1, so k times 1. And then you just leave it. ln 1/2. Could you write ln 1 minus ln 2? Yeah, I suppose. Matter of fact, I'm curious. Type that in your calculator. Type ln 1/2 in your calculator. I have a sneaky feeling it's not going to say ln 1/2. Maybe I'm wrong, but. And put a 1/2. Don't put a 0.5. Put a 1/2. What's it give you? Negative ln 2. I just dawned on me as I'm looking at that, because what did they do there?
Took out the -1.
They did ln 1. Well, they did. Oh, okay, yeah, I didn't even think of that. I was thinking that subtraction rule, right? If you've got a division inside of a log, it's the same as subtraction, right? I wasn't even, you're right, 2 to the -1, bring the power down in front. Or you could write ln 1 minus ln 2. And what's ln 1? What did we just say?
0.
ln 1 is 0. So 0 minus ln 2 would be negative ln 2. Okay, so they do that. Now, put in ln 0.5. Put in ln 0.5, what do you get? A decimal, right? That is one of the rules on the calculator in auto mode. If you have a decimal in the problem, it assumes you want a decimal answer, so it goes ahead and gives you a decimal answer. So if you wanted to force a decimal answer, if you wanted to do square root of 10 and you wanted a decimal, just put a decimal after the 10. Now, the other thing is just hit Control Enter. Hit Control Enter and you'll get a decimal, but if you do square root of 10 with a decimal, you'll get the decimal equivalent. Okay? All right, little tricks. Last one here. Yeah, well, yeah. Is that my, oh no, they looked at 60, 60. Okay, quickly. Here we get a situation where we have two unknowns. Well, you might remember in algebra the whole idea of two equations, two unknowns. Let me cover some of this up. So in algebra you had something with two equations, two unknowns. And to be able to solve with two unknowns, you need two equations. So what they give you is two pieces of information. So here, instead of one unknown and giving us one piece of information, they gave us 2 points on this thing to help us find those two unknowns. So I put a 1 in for x, and I get a 5 out. And I put a 3 in for x, and I get a 10 out. Right? That's what that is saying. All right? So now what I have to do is I have to solve those somehow. But again, I've got two unknowns. I've got an a and a k. So what do I solve for? So what I did was solve them both for a. Remember that with lines and stuff, right? There was that whole thing, solve one for one variable and then substitute it into the other one, right? So I could solve one of these for a and then plug it into the other one, or I could solve them both for a, set them equal to each other, right? That's what's going on here. Okay, so solve for one of the variables and substitute kind of thing. So I went ahead and did this. I solved them both for a. Probably not the smartest way to do it, but I did that. So I divided by e to the k, and on this one I divided by e to the 3k. Okay, so that's what a equals. So then those two have to be equal to each other. Now I could have just taken this and plugged it in over here. That probably would have been a little smarter. Okay, just taken this and then just plugged it in right there. But let's say I've done this. So I've got them both equal to a, so I set them equal to each other. Okay? So now what I'm going to do is I'm going to kind of do a cross multiply thing, but not quite. I'm going to take this e to the 3k and multiply it over to this side. Right? I'm going to take e to the 3k, multiply it to this side, which will put it on top, and I'm going to divide the 5 over to this side. That make sense? So I'll multiply the e to the 3k over here. I'm going to divide the 5 down under here. So I end up with that, right? So I divided the 5 over to the right side, made 2, and I multiplied the e to the 3k, which put it up on top, like that. Which is what this would have looked like if I'd have done the substitution that I said I could have done. And then what's e to the 3k over e to the k? You subtract the powers, right? You subtract the powers. So e to the 3k over e to the 1k, you subtract the powers, you get e to the 2k, and now from here it's e, right? From now here is just what we've been doing. So a lot of you, again, you could just look at that and say, oh, this is going to be 2k equals ln2, right? That's just, if you just put that into exponential form or convert it into log form, that's what you're going to get. I went ahead and did the log of both sides. Again, bring the 2k down in front, which gives you ln e, which is 1. So we get 2k equals ln2, and then divide by 2, and we get k equals 1/2 ln2. And notice I didn't write that as ln2 over 2, which I sure could have. You divide by 2, but I like to use fractions. You'll see when we get into derivatives and doing some things that division is kind of a messy thing to deal with. So multiplication's better. So I'd rather do 1/2 times ln2 than do ln divided by. It just makes things nicer generally. And now you're supposed to find a also, weren't you? You're supposed to find k and a. So if we come back to one of these, like this one probably is easier. So we'd have 5 over e to the, what I have, 1/2 ln2 would equal a. Now I would actually let you stop right there. However, if you look in the back of the book or in my solutions manual, or if this was a multiple choice question, this would probably not be one of the choices. So what have we talked about we could do with this? What could we do with that 1/2? Move it in there as a power. So we'd have e to the ln of what's 2 to the 1/2? Radical 2, right? 1/2 power is radical 2, square root of 2. And what's e to the ln square root of 2? Isn't that just square root of 2? Remember what we were saying, they kind of cancel each other out? So the whole bottom is actually just square root of 2. Now I'm perfectly fine with that. Mrs. Andreessen, this is another thing that makes her mad when I tell her I'm okay with this, because she spends so much time working with you guys on this, is normally we don't leave a radical in the bottom, right?
Yeah.
So we could take radical 2 times radical 2, top and bottom, and we'd get 5 radical 2 over 2. So chances are on like an AP test, maybe that answer would be that, 5 radical 2 over 2. So you'd have to get from this, right? I took my K and I plugged it in there, and then you'd have to do this work, right? So knowing these rules of exponentials and stuff is useful in kind of these kind of situations, in simplifying and so forth. Okay? All right. And then finally on 66, this was really just kind of, just that x plus 3 was a little bit different, but it's really the same thing. We're just going to do the log of both sides. We're going to pull the x plus 3 down in front, right? But it's got to kind of be grouped here. And of course, ln e is just 1. So you get x plus 3 equals ln 7, and then just subtract the 3. Again, people want to run to their calculators and know what that is. Don't worry about it. ln 7, take away 3. That's it. Just leave. Okay, just leave. All right. Yes?
On 64, I got way different answers, but somehow when I plugged it back in, it worked.
Like what do you mean by way different?
K was equal to the natural log of 5 over the square root of 12.5.
5 over the what?
Square root of 12.5. And A equals the square root of 12.5.
Anybody else get that? Okay, you're
I
right.
plugged it back in.
Let me look at it. Let me look at it for you. Let me look at it. We'll see. We'll see what happened. Sometimes if you make a mistake somewhere and get this, and then when it goes back in, that, you know what I mean, that same mistake makes it come out. It's a weird way, but let me look at it. We'll see what happened. All right, let's go to Appendix G here. Let's go to Appendix G. Now, again, setting up these story problems. That, you know, a business major would have to take one calculus class, right? Most business majors in any field, if you're in the business college, is going to take one calculus class. Now, they usually have what they call an applied calculus or a business calculus that you can take, which focuses more on these kinds of problems, business-related story type problem, that kind of thing. It doesn't get into as much of the calculus that we do. If you went from this class and took applied calculus in college next year, if that's the calculus you need, you'll do really well. That's the kind of thing. And we will do some of these. We will do some business examples when we get to chapter 4. But bottom line is, what they tried to do in their parts A, B, and C is they were trying to help you, right? They were giving you a bunch of stuff. When we get to chapter 4, somebody got the book open? When we get to chapter 4 and we do our quiz, you're not going to get that part A, B, and C, right? What you'll get is the problem. Coffee mugs can be manufactured for 60 cents each at a price of $1 each. 1,000 mugs can be sold. For each penny by which the price is lowered, 50 more mugs can be sold. Let N be the number of coffee mugs, and I might tell you to let N, or I might not even say that. I might just stop where for every penny we lower the price, 50 more mugs can be sold. Find the price that will sell the most mugs. Boom. End of the question, right? And you do the rest of the work. Okay, so we want to find the max profit, right? Find the price that will, no, what did I say? Sell the most mugs? That will generate the most profit. That would be the question. Find the price that will generate the most profit. So you'll say, well, okay, I need a profit equation. If I want to maximize the profit, I need to write an equation for the profit. Well, what is the profit? Well, I need to know how much profit I make on each mug times the number of mugs I sell, right? I need to know the profit on each mug times the number of mugs I sell. Well, how many mugs do I sell? Well, they said I could sell 1,000 if I'm selling them for $1, right? If I sell them for $1, I can sell 1,000 through market research and stuff like that. They generate these kind of numbers. So if I sell them for $1, I can sell 1,000. But if I lower the price a penny, I'll sell 1,050. And if I lower the price another penny, I'll sell another 50, right? And on and on. So the number of so do you see where that comes from? Did I write that wrong? Yeah, it should be 50, shouldn't it? I was going to say, I looked at that and said, wait. So, all right. So, doesn't that make sense then? Now they said let X be the price reductions, right? So for every price reduction, for every penny, for every price reduction, I'm going to add on 50 to the ones I can sell. So it's 1,000 plus 50x. So it's important to understand what is X. In this case, X makes sense to be the number of price reductions. Okay, so that's the number of mugs that I'm going to sell. And I've got to multiply that by my profit per mug. Well, let's think about what they said. What's my profit? Well, they cost 60 cents to sell, right? So every mug costs me to make. It costs me 60 cents to make, right? Maybe that's materials and labor and all that stuff. So they cost me 60 cents. So my profit is going to be whatever I sell it for minus 60, right? Whatever I sell it for, I'll get that money in, but then it costs me 60 cents. So I got to subtract that off, right? And that's called revenue minus the cost. Revenue is the money I bring in. So $1, so if I sell them for $1, I'm going to make 40 cents profit, right? But if I sell them for 99 cents, I'm only going to make 39 cents profit, right? If I sell them for 99, but they cost me 60, I'm only going to make 39 cents profit. So every time I reduce the price, I'm going to lose a penny on the revenue I get. So that's this right here. So it's $1 minus a penny for each price reduction. And then I have to subtract off the 60 because that's what it cost me. So this is the profit for each mug. So that's what they wanted you to do in part B, was explain how that was the price or the profit per mug. Well, now if I multiply those two, that's going to be total profit. So that's going to be N of X times I called it little p. They didn't give it a name. They gave the first one a name, but in part B they didn't give it a name. I gave it a name for profit, little p, profit per mug. And big P is the profit total, right? So I just multiply those two together, that's it. And then they want you to graph that. It's a quadratic that's, I think it ends up being some sort of a quadratic, isn't it? It kind of goes up like so, right? And then you could trace, and you could whatever. And I don't really care about that at this point because that's when the calculus will come in, actually. When the calculus will come in is we'll take this equation and we'll do some calculus to it to find exactly when that maximum occurs. Okay, the maximum profit. All right, moving on. Number 20. Okay, then number 2 we kind of talked about in class. By the way, what was the domain and range? Because that's something we're going to focus more on today. What's the littlest d can be, the depth of the water?
0.
0. Would you put a square bracket on that or a parentheses? It can be 0, right?
Yeah.
So a square bracket. 0, what's the biggest d can be? 10, because then the tank would be full. So 0 to 10 would be the domain on the depth of the tank, problem number 2. What's the range? That's the volume. What's the smallest the volume can be?
0.
0 if there's no water in the tank. What's the biggest volume can be? 1,000 if it's full. 10 times 10 times 10 is 1,000. And then those would have brackets on them as well, right? So 0 to 1,000 would be the range. So domain and range is just the possible x values that will give you some output, right? And then the range is what are your possible outputs from the function with all the different inputs plugged in. Okay? All right. So I've skipped 11, we'll come back to it. So on 20, here's where when Mr. Erwiller, in physics class or science class, they make you write down the units. This is the key thing. When you get a problem like this, is knowing how to set it up can be determined by the units. When I read that, they wanted to know something about the cost per mile, right? They wanted me to write a function of the cost per mile as a function of the speed. So I'm going to use C, and inside I'm going to put V, which was they said the velocity that we drive the car. So V is the velocity. So when they say cost as a function of speed, what that means, the second thing is your input. So that's what goes inside. Just like when they said they want us to write the volume as a function of depth, that would have been that function right there. So when we write f of x, that's like saying f as a function of x. So the terminology, this assignment's really about terminology, reading the words and being able to translate it into math. All right, so here's what I did. I wrote down all the stuff they gave me, and I wrote down the units. So they told me that the car gets this miles of the gallon. They told me that we're going to drive V miles per hour. The guy gets paid $15 an hour, and gas costs $1.50 a gallon. So what I'm going to do is I'm going to look at those and I'm going to say, how can I put those together in a way that will give me dollars per mile? Well, let's take this one first. What would I have to put with miles per gallon? I want to end up with dollars per mile.
How many gallons of gas?
Wouldn't it have to be that?
Yeah.
If I put those two together, shouldn't I be able to get gallons to cancel?
Yeah.
And I want to have dollars per mile. Now I want to have dollars on top, so I'm probably going to need this one, right? First, so that would be $1.50 per 1 gallon. Don't you do this in some science class?
Yeah.
Isn't that like a chemistry thing? That's what I do here. So what do I need to have happen here? I need to have gallons cancel. How many humps does an M have? Okay. Don't I want gallons per mile here?
Yeah.
So wouldn't that be this flipped? So wouldn't that be 7, and down here would be 180 minus 2V? Right? And what do I got? I got dollars per mile. Now that was for the car, right? And I have to add to that then the driver, right?
Yeah.
So I have to add to that the driver. So the driver gets, so we got V miles per hour and we got $15 per hour. So I'm going to want hours to cancel, and I want dollars on top, so I better put the 15 on top, right? So $15 for 1 hour. And then here I'm going to want to flip this over, right? So I'm going to want hours here and miles here. So 1 over V, right? And so hours cancel hours. So so if you want to simplify that a little bit, so 150 times 7 would be what, 1050? Over 180 minus 2V plus 15 over V. Wouldn't that give me the cost in terms of the speed? Right? Function, the cost as a function of the speed, which was V, the velocity. But all I did was use the units to get that to work together, right? So I wrote down everything I was given in units. I knew what units I wanted to end up with, and so I just made it happen. Just made it happen with units. That can be a pretty good strategy for doing story prep. Okay? All right. Otherwise, that would have been really hard to come up with, I think. But it seems pretty easy now when you look at it that way. All right? So you're glad you signed up for chemistry. All right, let's take a look at number 11. Okay? So one of the things I told you, and I appreciate all those people that listened yesterday when I said you better have a picture drawn on number 11. There were a couple of you there that didn't. Look like you just had the answer from the back of the book written down. But that would be hard to get without some sort of a diagram and some other things going on. So this says, I always love this problem because, I'm just picturing this guy freezing, stranded in his snowmobile, trying to get to the gas station, and so he grabs his TI Inspire CX Cas and he calculates exactly, he looks at his GPS and okay, I'm 3 here, and now I'm going to use a little calculus to find out exactly where to go to get there the fastest, right? Which of course by then he's frozen and dying in the snow. But anyway, that is the goal of this problem. The goal is to find out what route he should take to get there the fastest. Okay, because here's his option. Now it said there was a road, he was due south of the road 3 miles. There was a service station on the road that was 6 miles east of his position. So east of his position would be perpendicular, so you had to be able to read into that. East of his position 6 miles. So here's the service station. So he's got option. He could walk all the way in the snow, that'd be the shortest, but it's slow. He could go straight up to the road, so he could walk the most distance on the road, which is faster, but it's longer. Or he could do some combination in between, and it kind of makes sense that there's some spot in there to be the best, right? There's some spot in there that would be the fastest. Obviously, I don't think that would be going backwards this way, right? So we can probably eliminate that. So let's just assume he goes here. Now they did help you a little bit by saying let R be the distance he goes on the road, right? So R is going to be his distance he goes on the road. All right? Well, what if R is 0?
That means he's going to go through the snow.
He's going to go straight on the road. So one question, did they ask you domain? But this would be a really good question. This would be a great quiz question for next week on a problem like this, and just ask you the domain. Well, the input value is R. They tell you later they want you to do the write a function as time in terms of R, right? So the domain would be what are the possible R values?
Greater than or equal to 0, less than or equal to 6, right?
So wouldn't it be that? The least distance he'd go on the road would be 0. That's if he goes straight to the service station. And the most he would go on the road would be if he went straight up and went the whole way on the road. Right? Again, we're assuming that he would not go backwards and go farther on the road, which would be silly. Right? So for this particular function, that would be our domain. Right? And again, you just ask yourself the question, what's the input variable, what's the smallest it could be, and what's the biggest it could be? That's how you get the domain in a situation like this. Anyway, back to this. So, we got to think, we want time. We want an equation that's time. Well, let's see, we have distance equals speed times time, right? I didn't want to use rate because I'm already using R for something. So the time would be the distance divided by the speed, right? And they told us the speed, I think, didn't they? They told us the speed, okay? So the distance divided by the speed gives me the time. So let's do this part of his trip. So this part of his trip, we know the distance, right? On the road, the distance is R, divided by his speed. What's his speed on the road? 4 miles an hour. So right there is his time that he's on the road. Okay, now what I'm writing is an equation, so I call it big T for time, in terms of R, so I put an R in there, right? That's why I don't like to use X and Y, because it's not always X and Y. So input and output. Here our input is R. All right, plus, so that's his time that he spends on the road. Now what about the time he spends in the snow? Well, we need the distance and the speed. Well, we know the speed. The speed in the snow is 3. Where on my picture is the distance in the snow? But where in my picture is the distance in the snow? The hypotenuse here. This is the distance he's in the snow, right? So I need something for this. Well, I've got a right triangle, so what I need is, what's this up here?
6 minus R.
Wouldn't that be 6 minus R? So from that and that, can I get the hypotenuse here?
Yes.
Pythagoras tells us that this squared plus that squared, so 9 plus that squared,
Equals R.
and then the square root of that. And I wouldn't even bother multiplying that out, because probably something as messy as this I'm going to do on my calculator anyway. So I'll just leave it like that. Why go through the bother of foiling that all out and everything? So that is the distance in the snow. So here we go. That'd be 9 plus 6 minus R squared. That's the distance in the snow, divided by 3, which is the speed in the snow. That gives me his time in the snow. So time on the road, time in the snow, add those together, that's his total time. Okay? Then we could graph, I don't know, did it say anything about graphing it? I don't think it did it? It just said write it. See, but that's all algebra there. There's no calculus to this, right? What we would do is then want to do calculus to find the minimum time. What should R be? How far should he walk on the road so that he gets there the fastest, right? And so we want to find the minimum of that function, all right? And so if you graph it, it probably comes down and then it goes back up. And there's some place where it's like if he went this way, it's too long, takes too long. If he goes straight to the service station, it takes too long because he's in the snow longer. There's some place in between here where it's an optimum. It's a maximum that you should do. But it's kind of a silly scenario. I mean, that you'd actually sit there in the snow and calculate this. But, it kind of shows you the point of what we would want to do. But the business example is very, you could really see that where you want to be able to calculate these types of things. All right. So, good. Anything that we left out of that? Fairly thorough. We will not normally spend that much time working on homework, but it's early and I thought that was important to get over some of those things. Okay, stand up for 45 seconds, get your book out while you're doing that, and we're going, if your book's not already out, and turn to chapter 1, section 1. Take a little stretch.
I can do that.
You see those kinesthetics?
There we go. So on page 2 here, it talks about a couple of graphs describing this hot air balloon. Okay? So the first one is the altitude of the balloon in feet versus time. So that means this is minutes down here and this is feet up here. And this one is the vertical velocity. So this is feet per minute over here. And again, this is minutes over here. So they're both from 0 to 8 minutes, so we can overlay them on top of each other. And they're both describing what's going on with the balloon. So all I really want you to be able to do with this is be able to answer some questions about the balloon based on what you see on these graphs. Okay, so the first thing I'd like you to think about is just visualize in your head the balloon. What do you imagine this balloon doing? Going, floating up and down. Do you imagine it floating across horizontal?
Yeah.
I mean, I'll be honest, first time I read this, that's what I imagined, right? I imagine it going up and down and just kind of floating along, right? But based on these two graphs, would it have to be floating along horizontal? Couldn't it just be floating up and down? Right? Because the velocity it gives us is just the vertical velocity, right? Which is just in one direction, right? It's horizontal, or excuse me, it's up and down velocity. And this just tells me how high it is. So that balloon actually could just be going up and down, right? Because if we put horizontal into it, then if you've been in physics and you get into vectors and horizontal components and vertical components, and that's more complex than we want to get into. So we just want to talk about one-dimensional motion, okay? On a straight line. So in this case, our line is a vertical. So it'd be kind of like on the y-axis, if you will, right? You might think of it that way. So just moving up and down. All right. So if I said, okay, when was the balloon at 5,000 feet? You might say what? And when did it say when the balloon took off?
5.5.
Did it say like at noon or something?
It just says.
I don't think it ever did it?
It just says it took off.
It just said it took off. Okay, so it went about half a minute?
It's like 2.2.
And 2.1, 2.2. Now there will be times here early in chapter 1 where we will absolutely just approximate off of a graph. And I'll give you some leeway there on approximating. That's all the information we have. Now if we had an equation to go along with this, right, then we'd want to do some other stuff and actually find maybe specific. But here all we have is that. So yeah, I'd say at 0.5, at t equals 0.5, and at t equals about 2.1 or 2.2, somewhere in that vicinity, right? Because we're looking for where it crosses, there and there, right? That kind of thing. What about And here's why it's important to think of the balloon as only going up and down. And what I might say is, when has, to emphasize that, I might say, at what times has the balloon's vertical movement stopped? Let's just imagine the balloon is going just up and down. At what times has it stopped? And I'm looking at this graph, by the way. And time, when I say when, so I want the t values.
1 and a third.
So you're looking there, right?
Yeah.
So the bottom line is you're looking at the peaks, right? Because if it's going up and then it goes back down, it doesn't have to stop before it can do that, right? Theoretically, it's got to stop just at least for an instant before it can go back down. But now let's talk about this graph. Where has its vertical movement stopped? Aha, aren't those the same? Isn't this value,
Yeah.
isn't that t value the same? And then this one here is that one. And then this one here is that one. And then this one here is that one. Because that's where the velocity is 0, right? Where it crosses the x-axis. So isn't that interesting? We were just talking about profit, and we were talking about maximum, and we were talking about finding the time, which is minimum. Well, that's what you kind of have here, some maximums and some minimums, right, on this graph. Some language we'll be using later on. And that seems to correspond where the velocity, this thing, hits 0. Okay, and then of course you can bring in the whole thing we've already talked about with slope, right? What's the slope of that, right? You think back to what we do with the door opening. What's the slope right there? What's the slope right there? 0. What's the outputs over here? 0, right? So you see kind of this connection there with slope and stuff. Now that's not going to be on our next quiz, but at least kind of looking ahead at stuff. But just be able to answer those questions, just be able to read the y values on a graph and be able to tell what they mean and what they maybe describe in a situation. Be able to describe a situation, or you've been given a description of a situation, and be able to answer some questions graphically. And then also, if we gave names to this, if this was the a function, for example, and I said, what's a of 7, you know, you'd be able to look here and you'd be able to estimate, oh, a of 7 is about, what, 1,700 maybe, or something like that, feet, right? Or maybe I ask, when is a of t equal, well, that question I asked a minute ago. Right? That's like asking for the y value, right? That's in function language. So when does a of t equal 5,000? Well, when t is 0.5 or, what do we say, 2.1 or 2.2, right? That would be like solving that equation. When is the output of the altitude equation 5,000? Okay? Well, at those inputs. Okay? So be able to do both directions. I give you an x, you can find the y. I give you the y, you can find the x off of the graph. So that's just function language. You'll be able to read that. All right. So there's going to be some of your homework dealing with that and those kind of situations. Let's keep going here. And so, and oh, it talked about how fast it was going. So we've already talked about that a little bit. The steepness, you know, the steepness of the graph is going faster. If it's not as steep, it's not. Okay, now another thing that they talk about in this section is the different ways you can represent functions. So we can represent functions with a graph. We know we can represent with an equation. They show you on page 3 a table of values. That can represent a function, right? Look at page, well, that's a bad example. Let's go over to page 4. Go over to page 4, and at the top of page 4, they give you the function k. Now, I should have put a picture of that up here, but I don't have it. Example 3 has a function k. Now, that's a function. And they don't give any description of it or anything. It doesn't represent any real world. It's just a bunch of points. But that's a function. Right? A function is just one input, one output. I guess we should mention that, right? The old vertical line test. Can a function have one input, have more than one output? No, right? I mean, the vertical line test says if you put in a number in for x, you only get one output, right? Now you can get that same output over and over again, like the sine function, right? You get 1 a whole bunch of times, right? It has a peak at 1 a whole bunch of times. But you put in one value, you only get one thing out, all right? Now, for that function, what if I said, what's the domain of that function? the k function at the top of page 4? Akshay, what do you think? No? What would you write down for the domain of that k function right there? You would just list those x values. Not between. You wouldn't say from -3 to 4, because it doesn't include the ones in between, doesn't include the decimals. That function is only, see what you're thinking is that's just a table of some of the values of the function. If I give you an equation like y equals 3x plus 2, and I make a table of values, that would just be representative of some of the values of that function. That would be all reals, that domain, right? Y equals 3x plus 7, because that's a line, and that would be all reals. But if you're just given that function and what's the domain, you would just write down those, I don't know, 8 values, whatever's there. You just write down those 8 values. That's the domain. And what's the range? The other 8 values down at the bottom, right? The k values, the outputs. That would be the range, right? So a function can just be something like that, a table of values, all right? Or it can be a graph. Now let's look at the bottom of page 4, and they have this picture here, okay? Piecewise function. One of the things you guys said that you were worried about or had a concern about in the course description was piecewise function. So on our first quiz, why not? I mean, you don't like them, I'm going to put them on the first quiz. Piecewise function. There's going to be one on there. There's going to be a picture like this, and you're going to have to write the function, the equation of that. Now, all a piecewise function is a function that is in pieces. That's it. So all we do is we write the equation of each of the pieces. Okay? All right, so with that said, here's something you might want to put in your notes. This is the equation of a circle. You need to know that. Okay, because what I'm going to do is I'm going to give you one very similar to that. There's going to be one in your homework today where the pieces are either line pieces, and we know how to do a line. That's y equals m times x minus a. We did Appendix C that had some of those problems. So here's how we do a line, and here's how we do a circle. Now the problem with the circle equation is it doesn't have y equals. So what we'll have to do is we'll have to put those values in, and then we'll have to solve for y. Now the values are h and k is what? What part of the circle is that? That's the center of the circle, and of course r is the radius of your circle. So you're going to have to find the center of your circle and put that in for h and k, and you're going to have to figure the radius of the circle and put that in for r, and that's your equation of a circle. All right, and then you're going to solve it for y, right, which is just going to, all you're going to do is you're just going to move this over, you're going to subtract that over, and then you're going to square root it, plus or minus when you square root it, because you got the top half of the circle and the bottom half of the circle, because a circle's not a function, right? Because a circle fails the vertical line test. So you're either going to have the top half or the bottom half of the circle. So it's plus or minus when you square root it, depending on which half you have. Positive's the top half, negative's the bottom half. And then you add the k over, and you got y by itself. And we'll go through that an example here. So you need to know those two things. All right, so let's do that for this. Now they've already got the answer for you, so don't look. All right, so I'm going to write, we're going to call this function f. I don't know what they called it in the book, but I'm going to call it f. And then we put kind of a curly bracket like so. And inside, so that's already our y equals, right? So that's our y equals right there. So whatever comes after the y equals is going to go inside the curly bracket. In the curly bracket, we just put all the pieces, starting from left to right. Now, a piecewise function has two parts. It has the equation, the y equals part, and then it has the domain. Because since it's in pieces, it only goes for a certain distance. Like it might only go from 1 to 3, that piece. And then the next piece might go from 3 to 5. And the next piece might go from 5 to 8. See what I mean? So you got to put in how long that piece is. And that's all a piecewise function is. It's just in pieces. Okay, so the first one I'm going to do is this line. So let's do all the lines first because those are easy. So I got this line right here. Okay, so what do I need to write a line? The slope and, well, the y-intercept, but actually I don't need the y-intercept, I just need a point. Right? All I need is a point so I can put in for a and b. right? So what's this slope? Looks like it goes down 3 over 2. So I'm going to do my work off to the side here, and then I'll put my answer up here. So negative 3 over 2 is the slope. X, and now I need a point. What point do you want? This one right here? So that'd be negative 3, 0. So that'd be x plus 3 plus 0, which I can leave that off, right? Now, I'm perfectly fine with you leaving it like this. You don't need to distribute this, but you can if you want. If you want to, it'd be negative 3 halves x minus 9 halves. I would just write it like that, but you don't have to, right? So now, we already have the y equals up here, right? The y equals is already here. So I'm going to put in my negative 3 halves. I'm just going to leave it the x plus 3. And then I'm going to put a comma or a semicolon or something. And now, where does that piece go? From where to where? Now, when I say from where to where, I'm talking about on the x-axis here. It goes from negative 5 to negative 3. So I'm going to put closing brackets, negative 5 to negative 3, right? That's what a piecewise function is made of. Write an equation for the piece, which again, it's y equals is already out here. So it's y equals that, and then that piece goes from negative 5 to negative 3. And we wouldn't say negative infinity. If there was an arrow on this, you know, like that, then we would have said negative infinity to negative 3. But anytime we have a graph that's boxed in like this, we always kind of assume it just stops there. Okay? All right. Let's skip the circle because that's the hardest part. So let's go ahead and let's do this. So let's do this piece. So that's a line, and that's got a slope of what? 1. And then we need a point. You want to use that point?
Yeah.
So that point is 1, 0. So it'd be x minus 1 plus 0 again. So that's just y equals x minus 1. That's an easy one, right? So over here, I already got my y equals. I'm going to leave a space for my circle. So I got y equals x minus 1. Put myself a comma. And that goes from 1 to 3. Right? X value of 1 to an x value of 3 right there. So we're only looking at the x values. That's the domain we're putting in. The domain. Okay? All right. And then I got a piece here. Now it's possible that in your thing you have pieces, or you have gaps. Right? I mean, it's possible that there might not even have been anything here. Right? And we'd have just had a gap. We'd have went here to 1, and then we'd have went from 3 to 5. Because another question I might ask you is, what's the domain of this piecewise function? Well, this one is from negative 5 to 5, right? Because it's got values all the way from negative 5 to 5. But if there was a gap there where there was nothing, then our domain would have been from negative 5 to 1, and then from 3 to 5. Does that make sense? So we'd have had a gap there in our domain. But in this case, it goes all the way. Or if there'd have been an open circle maybe here, right? You know, that open circle kind of situation? Maybe there'd have been an open circle there. Well, then we would not have included this 3, right? And our domain would have been negative 5 to 3, not inclusive, and then from 3 to 5. Or you could have said negative 5 to 5, except x cannot equal 3, or something like that, right? So it's possible you got some gaps in there. But in this case, we don't have it. All right, let's do this last line. So the slope of that is what? Now make sure you do negative 1, right? Make sure you put your negative on there. That's important. And then what's our point? Want to use this one again? The one on the x-axis is nice. So 5, 0. So that'd be x minus 5 plus 0. Right? So if you want to distribute that through, it'd be negative 1x plus 5. I guess, but I'm just going to leave it. So I got negative 1, x minus 5, right? And then that goes from... Now, if we included the 3 on the other piece, we really shouldn't include the 3 on this piece. It doesn't matter which one we include it on. We just really shouldn't include it on both. Now, it doesn't really matter since it takes off it leaves this one and takes off this one at the same spot, but it's possible you have a piecewise function that comes in like this and then takes off from up here. You see what I mean? Then it's really important that you would include it on this one and not include it on this one, right? Could both of those be filled in?
No.
That would fail the vertical line test then, right? You can't have two values for this one input here, right? So we would not be able to have both of those filled in. And that's why we really shouldn't include both. So here, since I included the 3 there, I really should not include the 3 here. But I do want to include the 5 there at the end. So that piece goes from 3 to 5. All right, now we need to do the circle. So we've memorized, at least by Tuesday, next Tuesday, we'll have memorized the circle equation. So what is the center of this circle? Would it be there?
Yeah.
Okay. So its radius is 2. Its center is -1, 0. So I'm going to have x plus 1 squared, right? Because it's x minus h, so it's x minus -1 plus. Now, I'm going to put y minus 0 squared in my example here because it's fortunate that we had a 0 for our y, because that's going to make solving for y easier. So I want to give you a sense of what would happen if there was actually a number there. What would this look like? So I'm going to work it out with the -0 in there. Okay, even though if I was doing this myself on a quiz right now, it wouldn't. But I'm going to do that. So it'll be y minus 0 squared equals 2 squared, which is 4. Right? Now, I cannot just stick that up in here because this is y equals. Right? So I've got to solve for y. So I'm going to move that chunk over. So I've got y minus 0 squared equals 4 minus this quantity. There's no need to FOIL that out and try to simplify. I mean, you can, but there's just no need to do it. Okay? Now I need to square root this. So I get y minus 0. Now, you always, when you square root an equation, you should always do plus or minus. In this case, which one do we want?
Minus.
The plus or minus represents the top and the bottom half of the circle. This time we want the minus because it's the bottom half of the circle. Now, what if, remember I talked about what if there were some chunks missing out of here? What if there were some empty chunks? So what would have happened if this chunk wouldn't even have been on here? Okay, I just would have been dealing with this quarter, or no, let's say I did that. Let's say we would have went, this chunk wouldn't even have been here, and we only had this part. Then what would we have wanted as far as the plus or minus? Does that affect? Because I said top or bottom half. Well, that's not really the bottom half. It's only part of the bottom half. You still want the negative, right? How would we tell it that we don't want the whole bottom half?
Your domain.
That would be in this domain section. That would take care of that, right? And would you ever have part of the bottom half and part of the top half? It wouldn't be a function, right? It would fail a vertical line test. So you'll never have part of the bottom half and part of the top half.
Well, what if it cuts off at like -1 and then picks up on the top half at like just greater than negative?
Oh, great question. What if this part went down to here and then it picked up what, here?
Yeah.
And went like that? That'd be a different piece, right?
Okay.
So that's two different pieces. So what you would do is you'd have the negative square root as one of your pieces, and then you'd have the positive square root as another piece.
Okay.
Yeah, yep, just be two different pieces. Okay? All right, because you're right, that would be okay as far as a vertical line test. All right, let's keep going with this now. So we're going to go negative square root of 4 minus the quantity x plus 1 squared. Now, if you're having any bad thoughts right now, if you're having any bad thoughts, here would be a bad thought right now that I could do. Oh, for example, if I do the square root of this would be a bad thought, right? That the square root of x squared plus y squared is just x plus y. That's bad. That doesn't work, right? I can give you a real simple example why that doesn't work. Here's 9 plus 16. What's 9 plus 16? 25. What's the square root of 25? 5. If you were having bad thoughts, you would think that maybe you could just turn that into 3 plus 4, right? What's 3 plus 4? 7. That is not 5. It does not work. So when you have a plus in there with a square root, you can't do it. Because sometimes people think, oh, I'll just square root the 4 and get 2. And I'll square root this and get x plus 1, and then that'll be nice. No, cannot do that. Okay? So that we keep that way. Matter of fact, some of you might have been having those thoughts I didn't even think about back here. You might have been thinking here, oh, we could just do the square root of that and the square root of that. No, 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 no. Okay? All right, back to this. And then the reason I kept this minus 0 on here is we're not quite done, so we would add a 0 on. Usually where we add that on is onto the front end, so it'd be like 0 minus the square root. You know, it doesn't matter. You can add it onto the back end, the right end too. But that's where you would put that on. Okay? But in this case, you just leave it off. Okay, so that would go up here. So we would have negative square root 4 minus x plus 1 quantity squared. I don't know if that's how the book wrote it. I think that is how the book wrote it, wasn't it? And then that goes from what? Now we already included the negative 3 here, and we already included the 1 here, so we shouldn't include either one of them. Okay? And that's just because we skipped it and came back to it, but I could have included the 1 there and not on the next one. That's how you do a piecewise function. Just do the pieces, write the equation, so we know how to write a line. We need a slope and a point, and we now know how to write a circle equation, and we got to get y equals and we put it in. Okay, so you will have one on the next week, like that. You'll get a picture like that, and you have to write an equation like that. So there's at least one in your homework, I think, and we'll probably try to practice one before the quiz too. All right. I think that's all I got. So, that's a good thing, because we're about out of time. So, I apologize for not giving you a little more time to work, but your assignment is the 1.1 on the assignment sheet. Okay? 1.1. This is not due until Friday, this thing I'm handing out to you. It is, and we'll see, I might even, you know what? Let's make it due Monday. Yes. Let's make it due Monday. Yeah. Let's make this due Monday. It's not a huge deal, but it's what it is just a scavenger hunt for your calculator. So in other words, it's going to force you to get into some menus and look up some things. Just help you to get familiar with your calculator. So I want you to fill these things in, answer the questions kind of on there and do them, and then we'll just turn it. It would be a short, really small, couple point, 5 point something. It's mostly a completion kind of thing, but it just makes you get onto there and do that. So 1.1 homework on this sheet now, not right. I always get somebody who thinks, oh, I thought I was supposed to do all of them. Okay, it's always on this assignment sheet. Okay, so 1.1 for tomorrow.